the neutral axis. Right? So then we are going to sketch our element. So over here, this is the element H. Over here, this is our element K. So we're looking at a plan view now. And I'm just going to look at one force, which is the 200. Okay, I'm just going to look at the 200-pound force. Okay. And the distance to the 200-pound force, we are aware that this is the distance from here to here. Okay. And that distance over there is 10 inch. Okay. Okay. So the moment about y now, okay, moment about y acting on element H and element K, right? So my is equal to 200 multiplied by 10, which is equal to 2,000 pound inch. Okay, so you guys will say, hey, Eugene, don't really see the difference. Okay, so the difference is this. Okay, I want you to look at this. If the force, or when the force vector is parallel to neutral axis, okay, distance is between force vector, okay, force vector to neutral axis. Okay, first thing, right? So you can see for this case, the applied force is parallel to the what? Neutral axis. The one below, right, is when force vector is perpendicular to neutral axis, then the distance is between force vector to element. Okay, so for this case, the applied force is perpendicular to the neutral axis. Okay, so I'll put down here neutral axis. Then the distance is between the force to the element. Okay, so this is the difference. A lot of times the students will make the mistake here. They always consider, okay, let's do all towards the element, because the element is wrong. Okay, it depends if the applied force is parallel to the neutral axis or not. Okay, then you take towards the distance is between the neutral axis, or the distance is between the element. Okay, okay, so these are the critical paths for analyzing compound loading, and that's where we stop the last time. Okay, so we have dealt a lot with normal stress, we have dealt a lot with bending moment and shearing force. The thing that we have not done yet is the torque. Okay, is the torque. So the confusion part is, when is it a torque and when is it a moment? Okay, so let's look at the formula. Okay, so we know that moment, as mentioned before, is equal to force multiplied by perpendicular distance. We are also aware that torque is equal to force multiplied by radius, right? So the confusion, or the confusing part comes in is the radius is also the perpendicular distance, right? I'll quickly sketch an example. So now if we have a shaft from the front view, okay, if we have a shaft, right, shaft, this is the center, right? And then over here, this is our applied force, right? For example, this is our applied force. The radius is this distance over here, right? So this is so-called our radius. So applied force, and this is our radius. And this is also 90 degrees. So it's perpendicular, right? Okay, so when is it a force and when is it a moment? So let's focus on when is it a torque. Sorry, when is it a torque and when is it a moment, not when it's a force and when it's a torque. I do apologize. Okay, so the next thing that I'm going to do is I'm going to take the diagram. Okay, we have not analyzed another view last week, so I'm going to take this view. Okay, and then now we are going to analyze in the YZ plane. Okay, we're going to analyze this in the YZ plane now. Okay, so I'm going to sketch Y YZ plane on. And then this will be our rotation in the X. Okay, so I'm going to draw this, sketch this out. Okay, and then this is our shaft. It should be a chain line, okay, but I don't have chain line. I just go draw a solid line. And then next we're going to put in our applied force, or we draw our element first. Okay, so over here, this is our element H, and over here, this is our element K. Okay, so that's our element K. Then we put in the associated forces. We have a dot. The force is coming towards us at 150. We have a force coming down here at 200 pounds. Okay, and then we have two forces over here coming in at 150 pounds and 50 pounds. Okay, and then very important, we're going to sketch the position of our neutral axis. So now our neutral axis is a dot, right? So this is our neutral axis. Okay, so again, the neutral axis, the sketch is over here. That is the position of our neutral axis. So the only force that, so there, okay, the forces, the only force that we have to consider for this case is the arrows, right? The arrows. Okay, so if we do, we have done this before already, but I'm just going to do it again. If we are going to do summation of forces, in the, or summation of forces in the Fy, or we're just going to do the Fz direction. Okay, so you have 150, or sorry, not, this is not Fz, this is relative. We're going to do the Vz. Okay, so this is 150 plus 50 minus by 200. So this is equal to 0, which we have done it before, okay, last week. Now, the next thing is this. Is the 200 pounds going to induce a moment or torque? Right? Remember, both formulas are very similar. It's force multiplied by perpendicular distance for moment, or force multiplied by radius for torque. Okay. So whether is it moment or torque, you observe the deformation pattern of the neutral axis. Let me write this out. Whether whether, no, this is not the whether. Whether, what am I doing? Whether it is moment or torque is dependent on the deformation pattern of the neutral axis. Okay. So with this view, I'm going to draw the deformation pattern induced by the 200 pounds. Okay. So the 200 pounds is going to induce a deformation pattern looking like this. This is just a sketch. Okay. Okay. So this is where the 200 pounds is acting on. Okay. And I'll write this as the deformation pattern. And what you see over here, the neutral axis still remain in the same point. Yes or no? Okay. So when that is the case, when the neutral axis, okay, I'll write down note, during loading, when the neutral axis did not change position, okay, the the load is known as torque. Okay. Now let's view this